In our previous session, we talked about how measurements are inexact numbers because they will always have uncertainty or ambiguity associated with them, or an error associated with them, which comes from the instrument. No matter how perfectly the instrument is functioning, every instrument is designed to only report a measurement to a certain degree of precision. So the measurements that we record using those instruments can only have that degree of precision. In other words, there's always room to have a more accurate measurement of the property being measured. So, continuing from that point, this leads us into the idea of significant figures in measurements. Significant figures are significant, meaning important, because they give us the error in a measurement reported. And significant figures are important every time you deal with measurements. Anytime you record something with the use of an instrument, significant figures is something that we have to consider and keep in mind. Significant figures are defined as all the certain digits and one uncertain digit. The uncertain digit that's at the end, the last digit, is the estimated digit. This is where the error lies. The error always lies in the last reported significant figure, and that's very important for us to remember. Okay, so how do we determine the number of significant figures in a certain measurement? The rules are all non-zero digits are always considered to be significant figures. Zeros may or may not be, depending on the category they belong to. Zeros can either be leading zeros. Those are the zeros that are in front of the first non-zero digit, and leading zeros are never significant figures. They're good, they're important as placeholders, but they are not important as far as error is concerned. Confined zeros are those zeros that are sandwiched between two non-zero digits, and confined zeros are always considered to be significant figures. Trailing zeros are the zeros that follow the last non-zero digit in a number, and trailing zeros are significant figures only if there is a decimal point somewhere in the number or an overbar above that trailing zero. If neither exists, then the trailing zeros are not significant figures. Now I want to address this whole idea of overbar. In math, you've of course come across the overbar, but the meaning is different. In math, when you see, for example, 3.3 with an overbar, it implies that the last three, the second three, can be repeated infinite number of times. But this is the meaning in math. But that's not the meaning that is conveyed by the overbar above a trailing zero in this context. Let's say we have a number 300. And if the number 300 has an overbar above one of the trailing zeros, then that means that this zero is a significant figure, while the other zero isn't. Let's say we wrote the number 300 but with an overbar above both the zeros. Then both the zeros will become significant figures. So the meaning is different. Now, because of this difference in meaning between the two fields, I guess, we are moving away from overbars. You will not come across overbars very often. In this context, in the context of significant figures, there are better ways of representing a measurement in the correct number of significant figures without using the overbar. Okay, so let's use this table to figure out how many significant figures each of these measurements has. Now please remember, non-zero digits are always significant figures. Leading zeros are never significant figures, but there are no leading zeros here, so we don't need to worry about it. Confined zeros are always significant figures. Trailing zeros are significant figures only if there is a decimal point somewhere in the number or an overbar above a trailing zero. In this case, neither exists, so none of these trailing zeros will be counted as significant figures. So now if you add up the total number of significant figures, we have 6 significant figures. Using the next example, once again, leading zeros are never significant figures. Non-zero digits are always significant figures. Confined zeros are always significant figures. Trailing zeros are significant figures if there is a decimal point somewhere in the number. So this one is a significant figure. If you count the total number of significant figures, once again, there are 6 significant figures. So using the same idea, let's go through the rest of the list and determine the number of significant figures. 2, 5, 5, 5 again, 4, 3, 1. Now in the next 300, I intended to actually put an over bar above one of the zeros, which then makes this number have 2 significant figures. This one has 3, and this one has 2 as well. Now, why is it important for us to know how many significant figures a certain measurement has? It's important because, as you remember from the previous slide, the error in a measurement lies in the last reported significant figure, which means that if this is the last significant figure in the reported measurement, then the error will be, in this case, 2, 3, 4, 5. Whereas in the next case, the error will be, since the last reported significant figure is the trailing zero, will be 1, 2, 3, 4, 5, 6, 7, 8. The trailing zeros in this case are not significant figures, so the error is plus minus 1000. Next one is plus minus 1. I hope you see the difference that a single dot makes in how the meaning that a measurement conveys. In the first case, there are 2 significant figures, and look at the error. The value can be anywhere between 14,000 and 16,000. Whereas by simply adding a decimal point at the end changes the number of significant figures, which therefore changes the error. In other words, here the value is between 15,001 and 14,999. So because the error changes the meaning that a measurement conveys, the precision that the measurement is conveying changes completely as well. So the error in this case will be plus minus 1, plus minus 0.123456 1, plus minus 0.1, plus minus 1, plus minus 100, plus minus 10. Once again, compare these 3 ways in which the number 300 is written, and notice that the difference is the error in case of each of those measurements. Plus minus 1, plus minus 10. So it's very important that we write the measurement in the correct number of significant figures as allowed by the instrument, which is what we'll talk about in next slide. It is not us who decides how to write and report a measurement, record a measurement. It is the instrument. We have to see how the order of precision that the instrument allows us. When you are recording the measurement using a certain instrument, you must record all the certain digits and only one estimated digit at the end. What does that mean? Let's take a couple of examples to understand that. So let's take an example of an instrument called a graduated cylinder. This is an instrument that measures the volume of a liquid, and it has graduations or calibrations on the side that we must read correctly and report that measurement. Let's say that this graduated cylinder is designed to read volumes in this way. That's the calibration. And this contains a liquid with the level of the liquid being right there. And you are given the job of reporting this measurement. Now, please understand, whenever you're reading such instruments that have calibrations on the side, we must report all the certain digits. Certain digits are the digits that you can read directly off the instrument. So in this particular case, this is a certain digit. We know there is 2 mLs, but we also know there is a little bit more than that, or something that we need to estimate. There must be one estimated digit at the end. So I might estimate that to be 2.2 mLs. My neighbor might look at it and say, no, that's actually 2.3 mLs. Or maybe somebody says 2.25 mLs. Or someone says, no, you guys don't know what you're talking about. This is 2.249 mLs. Who is correct? According to the rules, we must report all the certain digits. So if the graduated cylinder has calibrations as shown, then this is a certain digit. There is no certainty about this digit. But the next digit, given the calibrations, is an estimated digit. We are only allowed one estimated digit. We are not allowed more than one estimated digit. So this is the estimated digit. We must have one, but not more than one. So which means that this is not the correct way of reporting the volume in this graduated cylinder, nor is that. What if the level of the liquid was instead right there? How would you record that volume? Once again, you must have all the certain digits and one uncertain digit. Something's going on. Let's fix that. So this would be 2.0 mLs. This 0 is where the error lies, and therefore this 0 is very important. Now let's assume that we change the graduated cylinder. It is slightly different in that it is not only capable of reading every 1 ml of the liquid, but it is also calibrated to read 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these calibrations are different from the one before. And now if the level of the liquid is right there, how do we report? Once again, you must have all the certain digits. So 2 is certain, but this time the next digit is also certain because we can read it directly from the instrument. We don't have to estimate at all to say that there is 0.2 as well. But there must also be one estimated digit which is estimated. So in this particular case, these are the certain digits which are read directly from the instrument, and the last digit is the estimated digit or the uncertain digit. This is where the error lies. So if we are using the second graduated cylinder, the error in the measurement will be 0.01 ml, in other words, in the second decimal place. So it's very important to read the calibrations on an instrument such as this and record the measurements in correct number of significant figures. Okay, so oftentimes we measure properties and then we do mathematical calculations involving those measurements. So here's an example where, assuming all the numbers are measurements, you need to carry out the following calculations using a calculator, and please report all your calculator answers. Don't make any changes. You might want to pause the recording for a minute while you finish that. Okay, assuming that you're done and hopefully your answers match mine, here are the calculator answers that I got. Now, when you are calculating using measurements, how do we report our final answers? Do we just report it as the calculator gives us? No, we can't. Our answers cannot be more precise or more accurate than the least precise or the least accurate measurement used in the calculation, which basically means that when you are multiplying or dividing, your answer needs to be in as many significant figures as the measurement used in the calculations with the fewest number of significant figures. On the other hand, if you're adding or subtracting, then your answer needs to be in as many decimal places as the measurement used in the calculation with the fewest number of decimal places. So, in order to satisfy these rules, when you are calculating using measurements, we have to oftentimes round off our answers. The rules for rounding off will be very straightforward. If the first digit to be dropped is less than 5, the last retained digit is kept as such. However, if the first digit to be dropped is 5 or higher, then the last retained digit is increased by 1. So, as an example of the use of these rules, let's say we have a number 5.6250. Currently, this number has 5 significant figures. But let's say we need to round this off to 3 significant figures. In other words, we need to round it off right there. This is our last retained digit. That is our first digit to be dropped. So in this case, the first digit to be dropped is 5, which means that the last retained digit gets raised by 1, and this number now has 3 significant figures. What if we needed to round the number to 2 significant figures? In other words, we needed to round off right there. Now in this case, it would be 5.6 because the last retained digit is not changed as the first digit to be dropped is less than 5. Okay, so let's go back to the answers that we calculated earlier and decide how many significant figures or decimal places each of those answers needs to be given in and do the rounding. Okay. So in case of the first one where we are multiplying, we need to focus on significant figures. This number has 5 significant figures, whereas this one has only 2 significant figures. Therefore, the answer should be in 2 significant figures rounded off to 2.6. Second one is a division. Once again, we focus on sig figs, and in this case, the numerator is 6 significant figures, whereas the denominator is only 3 significant figures. So our answer should be in 3 significant figures as well, gets rounded to 54.2. The third one is a combination of multiplication and division, but in both of those cases we focus on sig figs, and if you look carefully, this number right here has 1 significant figure. So our answer needs to be rounded to 1 without changing the order of magnitude. This is 2,832, should be rounded off therefore to 3,000. Now be very careful how you write this answer. Do not put a decimal point anywhere because that will change the number of significant figures. Okay, the next 3 examples are addition or subtraction, in which case we are not focusing on sig figs, we are instead focusing on decimal places. So since this number has no decimal places, we'll round off our answer to 0 number of decimal places as well, which makes this 1,261. This measurement has 1 decimal place, so the answer gets rounded to 1 decimal place as well. And once again, this one has no decimal places, so we round off our answer to 4,603. No decimal places as well. Okay, so please remember that when you multiply or divide, we need to focus on significant figures, but when you add or subtract, we need to focus on decimal places. always the least number possible. Okay, what if you are dealing with a question such as this? Now, this is a slightly different question than before because it not only has a measurement, but it also has a counted number. In other words, in this particular case, 130 textbook is a counted number, whereas 2.351 pounds is a measurement because that is determined with the use of a scale, an instrument in this case. The counted number is an exact number, but a measurement is an inexact number. When you carry out such calculations, the exact number, the counted number, does not affect the number of significant figures in the answer, which basically means that if you were to multiply the two numbers to get the mass of the total pile, the entire pile of textbooks, you would get that as the answer. Now, should this answer be represented, the final answer be represented in two significant figures because of 130 textbooks, or four significant figures because of 2.351 pounds? Yes, absolutely. Four significant figures because that is a measurement. 130 textbooks is a counted number, and that does not affect the number of significant figures in an answer.